Hello, today's video is section 4.4, asymptotes. There are two kinds of asymptotes that we will work with in this class. Vertical asymptotes and horizontal asymptotes. I think you've probably seen these before. Vertical asymptotes, graphically at least, look something like this. Typically they're represented with a vertical dotted line, maybe at like x equals 3, say. And so since it's a vertical line, the equation is x equals a number. And so maybe here's an example of a function that has a vertical asymptote at x equals 3. Okay, the black curve is a graph of my function. As you can see, the function is undefined at x equals 3, and the arrows here are supposed to indicate that the function is approaching infinity, just growing arbitrarily large when I'm smaller than 3, and when I'm close to 3 but larger than 3, the arrow tells me that my function seems to be getting arbitrarily large, but in the negative direction. So the definitions for vertical asymptotes are in the book. X equals 3 is a vertical asymptote. I'm going to often abbreviate that as VA. If, for example, the limit as x goes to 3 minus of the function f of x is equal to infinity, or could be minus infinity. There are other options here, right? Maybe my limit as I go to 3 from the left isn't infinity or minus infinity, but maybe my limit as I go to 3 from the right of the function is equal to either plus or minus infinity. Right, so the point that I'm trying to make is that a vertical asymptote is defined in terms of a limit. In other words, when your function has an infinite limit at a certain x value, x equals that x value is the equation for the vertical asymptote. The other kind of asymptote that I talk about in this section is something called a horizontal asymptote. Graphically, we might be picturing something like this. In the xy plane, horizontal asymptotes, as you might imagine, can be represented with horizontal, with dashed lines. It's not necessary that one is above the x-axis and the other is below. Some functions don't have any horizontal asymptotes, but they could have at most 2. So here's an example of a function that does have 2 horizontal asymptotes, right? Maybe the graph of my function y equals f of x looks like this. And the idea with the arrows in this case is that as my x values get large but negative, maybe the function approaches the height y equals -7. Out here, right, toward the kind of end out here, when my x values get really large but positive, maybe the function values approach a height of y equals 6. So y equals, let's just say 6, for example, is a horizontal asymptote. That's an HA. If one of the two following things happen: if the limit as x goes to infinity of f of x is equal to 6, or if the limit as x goes to minus infinity of f of x is equal to 6. So this notation is slightly different from limit notation that we've seen before, because here the x, we're thinking about the x value as getting arbitrarily large, or x is going to infinity. On the other hand, maybe x is going to minus infinity. These are called limits at infinity. And they're not the same as infinite limits like we have for vertical asymptotes. When I think of horizontal asymptotes, I think about what's called like the end behavior of the function. Because the horizontal asymptote is telling me kind of like what's happening sort of way far out on either end of the function, when x is really super large or when x is really large but negative. Let's take a moment and look at a specific example. Let's think about the reciprocal function f of x equals 1 over x. We've seen this one before. You might remember that the graph of this function is the basic hyperbola in the first and third quadrants. From the graph, we can see two things, or well, maybe three things. First of all, notice that the y-axis here, in other words, x equals 0, is a vertical asymptote for this function. Okay? In particular, the limit as x goes to 0 from above of 1 over x is equal to positive infinity. Okay, right here, where my function increases arbitrarily large as my x value gets close to 0. And this should make sense, right? If I think about dividing 1 by smaller and smaller numbers, the actual fraction gets larger and larger. Okay, etc. On the other hand, right, if I were to divide 1 by smaller and smaller numbers but negative, the magnitude of these numbers gets larger and larger, but the sign is negative. Okay, and we can represent that by writing the limit as x goes to 0 minus of 1 over x is equal to negative infinity. Another thing that we should notice about the function 1 over x, or the graph here, is that we have a horizontal asymptote. Okay? The x-axis, in other words, y equals 0, is a horizontal asymptote. Okay, out here, this end behavior out here, shows me that the limit as x goes to infinity of 1 over x is equal to 0. Right, my height is getting smaller and smaller, closer and closer to 0, as I go further and further out in the x direction. In other words, when I divide 1 by bigger and bigger numbers, that fraction gets smaller and smaller. In the other direction, right, when x is really large but negative, the limit as x goes to minus infinity of 1 over x is also 0, right? If I divide 1 by, like, negative 1,000,000, well, that's really close to 0. It's negative, but it's still really close to 0. All right, so y equals 0 is a horizontal asymptote for the graph of y equals 1 over x. This kind of behavior happens for similar functions. In other words, if f of x is like 1 over x squared, what's the limit at infinity? As x goes to infinity for 1 over x squared, I have 1 divided by a really, really big number. It gets squared, so it's even bigger, and so that's 0. Right? Same thing for 1 over x cubed, 1 over x to the 4th, etc., etc., etc. So, this fact and this fact here come in handy, and I can use these to develop a strategy for computing limits at infinity of rational functions. Here's how this is going to work. Let's say my function f of x is equal to 4x cubed plus x divided by 7x cubed plus 2x squared plus 1. So this is a rational function because it's a quotient, it's a ratio here, of 2 polynomials, 2 cubics in this case. If I want to try to compute the limit as x goes to infinity of 4x cubed plus x over 7x cubed plus 2x squared plus 1, here's the strategy that I can take. First, I can find the largest power in the denominator. So in this case, the largest power is 3. And then I want to divide every term by x raised to that power. Every single term in the expression. So I should divide all terms by x to that power, whatever that happens to be. So in this case, since the x cubed here is my dominant term in the denominator, I divide every term by x cubed. Okay, what this amounts to is multiplying the top and the bottom by 1 over x cubed. Okay, and I know that if I multiply a fraction by a number divided by itself, I'm only multiplying by 1, and multiplying by 1, of course, doesn't change the value of the expression. So I'm allowed to do this division. Okay, when I do the division, let's see what happens. In other words, let's try to simplify here. X cubed over x cubed cancels. X divided by x cubed leaves me with 1 over x squared. In the denominator, the x cubes cancel there. This x squared cancels with all but one of those x's. And so I'm left with this. I'm left with the limit as x goes to infinity of 4 plus 1 over x squared, all divided by 7 plus 2 over x plus 1 over x cubed. The limit laws can be shown to still apply for limits at infinity. In other words, when I do the limit of a quotient, I can try to do the quotient of the two limits separately. And so now if I just think about what the limit is in the numerator, what's the limit as x goes to infinity of 4? Well, 4 is always 4, regardless of what x is, so that's going to stay 4. Okay, this is typically true for any constant function. 1 over x squared, on the other hand, we just saw on the front board, 1 over x squared goes to 0 as x goes to infinity. So in the numerator, I'm ending up with 4 plus 0. In the denominator, the limit as x goes to infinity of 7 is 7, because 7 is always 7, no matter what x is. 2 over x. This is just like 1 over x from a minute ago. If I divide 2 by larger and larger numbers, that goes to 0. Same thing for 1 over x cubed, right? Dividing by bigger and bigger x's, because x is going to infinity, would cause 1 over x cubed to go to 0. So in my denominator, I'm ending up with 7 plus 0 plus 0, and we can see that this is 4 over 7. So 4 over 7 is the limit of f of x as x goes to infinity in this case. It's a limit at infinity. And what I could say at the end here now is that y equals 4 over 7 is a horizontal asymptote for the particular function that I'm looking at. In this case, y equals f of x. 4x cubed plus x over 7x cubed plus 2x squared plus 1.